All right. Hi, grade 12. It's been a while since my last class. Sorry. It's not been easy for me to get these videos done for you for various reasons, but here is the next topic for our IB chemistry, topic 10 for organic chemistry. Now, before we get into the reactions for alcohols, we'll get there and it's a little bit lengthy, that topic. So I need to go back and review, actually not review, like teach you guys for the first time the reactions for alkanes and alkenes, and then we'll go into alcohols. So we are starting topic 10.2, okay? The functional group reactions in organic chemistry with hydrocarbon compounds. All right, so I am just going to show you my PowerPoint. All right, slideshow. Okay, so alkanes have low reactivity, and they also undergo free radical substitution reactions, which we'll be seeing a lot of in this first part of the lesson. And the reason why alkanes have low reactivity, okay, is because they have non-polar single bonds that cannot be eliminated easily. And because these bonds are non-polar covalent, they are hard to break. Now, so if you remember, okay, that in alkanes, our formula is CnH2n plus 2. And when we first learned how to name them and write their formulas. So if you remember, they belong to the homologous series where they are connected by only one single carbon to carbon bond. Make sure you remember that one. And and they're described as saturated hydrocarbons. Remember, because they have the maximum number of other atoms joined to them, like other hydrogen or carbon atoms, but with single bonds only. Okay. And alkanes, they lack functional groups. So the chemistry is restricted to combustion and substitution reactions. So they are fairly generally unreactive. So the two main reasons that you guys will need to remember for both paper 1 and paper 2 to why the alkane series are unreactive is the first reason is that the carbon-carbon and carbon-hydrogen bonds, or the carbon-carbon single bond and the carbon-hydrogen single bonds, do not break easily because they have a high, bond enthalpy, okay, which means that it's hard to break the bonds, right? So you can see that. Well, I mean, not super high, but they're high enough. And they also have a similar electronegativity that both of them, when you calculate the delta En, remember how to do these, remember? We get these from the periodic table and we calculate the electronegativity difference. So for carbon-carbon, it's 0 because they're identical, right? So they're identical and delta En is 0, so that's completely covalent, 100%. For a carbon-hydrogen single bond, okay? So this one is, when you do delta En, you get 0.4. So this is almost polar covalent because 0.5 to 0.7 is, 0.5 to 1.6 or 1 I can't remember. You guys remember that scale. That somewhere in the middle is like polar covalent, but this is quite close to being polar covalent, but it's still in the non-polar range. So either one of these are not very polar, okay? So, and yeah, so that's why, because of the little polarity, then that also means that they're not as reactive, okay? Right, so, and alkanes do not react with acids, no bases, no oxidizing agents. So the only thing that they really undergo is free radical substitution, where a hydrogen atom is substituted for a halogen. Okay. Let's see. Now, actually, let me show you. Let's see. How does that? Okay. Never mind. I missed a slide here. I think I forgot something. All right. Anyways, how does that even happen? So alkanes contain. Okay. So alkanes contain electron-rich sites between a carbon and hydrogen covalent bond. So the hydrogens have a partial positive or slightly polar, remember this, dipole, slightly positive charge because they are bonded to, okay, because the carbon is slightly more negative than hydrogen for sure in terms of electronegativity value. Okay? So because the carbon is slightly more negative, so that's why the electrons are drawn to itself, and this bond can be attacked by a free radical. Okay. So that means that this leaves the bond open for an attack, and that's why we call this a free radical. And I'll show you in more detail a little bit later what that is in the animation. Now, so a substitution reaction, just so you know, it involves substituting a hydrogen for a halogen. Okay, it's like chlorine, bromine, fluorine, whatever in group 7. So, and then in order to activate this reaction, we need UV light, okay, to break apart the bond in the halogen. So if we have, let's say, methane and chlorine, okay, we can mix those together with UV light, and then we can substitute a chlorine onto the hydrocarbon, okay, and then we form this compound, which is a chloromethane, okay, because you have a chlorine replacing one hydrogen here, and we call it chloromethane. You don't have to do it like 1-chloro. No need for that numbering system here, remember, because it's just one carbon in the whole thing. So we can just call it chloromethane. Right? And then the byproduct is going to be HCl, hydrochloric, okay? Because we substituted a hydrogen for the Cl to get that HCl, okay? So then again, this is known then as your halogenation. So they refer to this in your IB textbook as halogenation. So, and if we have chlorine, okay, if we have chlorine in this process, we call that chlorination. If you had bromine instead of chlorine, you would call it bromination, and so on, the way that you name those halogens. Okay? Now, this type of reaction takes place in 3 important steps called initiation, propagation, and termination. Okay, so we describe the substitution, okay, this substitution process that I just mentioned, by sequence of steps, and then we call them, your book refers to them as the reaction mechanism, which involves these 3 steps: initiation, propagation, and termination. Okay? You have to memorize this, you guys, for standard level, topic 10.2. Okay, now, okay, I will just briefly mention what these are. Then I will show you the animated PowerPoints that will explain it in full detail how it actually happens that you need to know in terms of the detailed mechanism to these 3 steps. Okay, so initiation, this one, okay, it's basically what it is. It's known as the photochemical homolytic fission, okay? So basically, what the heck that means is photochemical simply means the UV light, okay, that we need as a catalyst. Homolytic, okay, that just means splitting things into 2 equal things that are identical, homolytic. And fission, you might have heard of this before, which is also known as cleavage, is simply breaking the bond, okay, breaking it apart. So that you know what that means. Propagation is a middle step that you see. It can't really show to you. It's 2 main steps, actually, or 2 main parts, 2 main equations that make up that one step. So that's the middle part where things are rearranging more and duplicating. And then eventually termination will occur when the radicals collide with each other. That will form a unreactive product or molecule, okay? And that means absolutely nothing until you actually see how it works, right? So give me a second here, I stop sharing. Then I will just pop up the video on a website. Okay, why is this not logging in? Give me a second, everyone. Sorry, no video footage. Need to go to timeout. Okay, we'll show you now what we're doing. Okay, here we go to, we're gonna show this a little bit here. All right, before I show you that, give me 1 second. All right, before we get to the animation, okay. God dang it, it's always like this. Current slide. All right, okay. That's the initiation step I told you about earlier, okay? Then propagation step, where free radicals react with non-radicals, producing more free radicals and making a chain reaction. That's the middle process. And then termination step, where free radicals react with each other, producing non-radicals and terminating the chain reaction, the ending of the mechanism. So I'll show you it all at once, and then we'll go to the animation to see what happens, okay? So this is basically what this is, reaction mechanism. Initiation is this part. You create these free radicals, okay? And they break apart with UV light, thank you. And then so it breaks apart and you basically have individual broken up identical chlorine free radicals with a free electron in each of them. And then you have propagation, which is done in 2 parts, okay? And then the final part, termination, is when you have to end that, where there's stop production of more of these radicals to form a non-radical compound or molecule or element, okay? So you see it in detail now with the animated slides. All right, so let's start playing this. Here we go. So a free radical substitution involves highly reactive free radicals, like those chlorine dots you saw. So these are atoms or groups of atoms with unpaired electrons. Okay, so let's see what happens here with the UV light into this container. So when exposed to UV light, a mix of chlorine and methane undergoes a free radical substitution reaction. Okay, those 3 main steps: initiation, propagation, termination. So in initiation, the UV light is absorbed by a chlorine molecule and gives it the energy to break that bond. 1 electron goes to each chlorine identically and creating 2 free radicals. And that's your homolytic fission that I mentioned earlier. And many chlorine molecules are split by this homolytic fission. So the initiation step of the mechanism leads to a rapid increase in the number of free radicals, as you can see here. So propagation 1, first part of the propagation step, a chlorine radical reacts with a methane molecule, removing a hydrogen to create a methyl radical, which you see here, and of course, HCl, hydrogen chloride. And here's the overall reaction there. That's propagation part 1. propagation part 2. A methyl radical reacts with a chlorine molecule, creating another chlorine radical and chloromethane. Okay, so here's your new chloromethane. And during this propagation, the total number of free radicals remains the same. And here is its overall reaction. Now in termination, there's also different parts. First part of termination of a free radical substitution reaction, the total number of free radicals decrease. So for example, a chlorine and methyl radical, okay, can react to form this chloromethane. So this is one way to end it. Another kind of way to end, okay, the mechanism is when two chlorine radicals react to form just diatomic chlorine molecule. And the last way that you can end the termination is when two methyl radicals react to form C2H6 ethane, which is usually unreactive. Okay? So in summary, these are all of them together: initiation, propagation in 2 parts, termination. I wouldn't say that this is done in 3 parts like propagation. Don't be confused. With the termination, there are 3 possibilities of how it can terminate. So propagation is like 1 and 2 different parts, but termination is more like it either will end with this one or this one or this one. Be very careful with that with termination, okay? It's not necessarily done in 3 different parts. It's more like one or the other of these 3. But propagation, both of them are going to happen, all right? I hope that makes sense now for reaction mechanism. Okie dokie. Let's get that one out. Let's go to a different slide. Give me a second. Oh, God, I keep losing track of how to share the screen. All right. Slide 36. I am confusing myself. It's not funny. Okay. Now, if you can see this. Okay, let's just do this. Review what you just saw again. Okay. There we go. Okay, so you can take a snapshot of this as well. It's another way that you summarize what you just saw earlier in this animation, okay? Initiation, homolytic fission. Each chlorine atom receives one of the electrons in the single chlorine-chlorine bond, okay? Then the propagation is 2 different parts, okay? The radicals then react with methane molecules. In the process, a methyl radical is produced. The methyl radical reacts quickly with the CO2 molecule, okay? Which is just like you saw in the animation. And finally, the termination. The process is terminated when 2 radicals react together to make a relatively unreactive molecule. So again, like I said, it's not necessarily 3 different parts in sequence. They're just 3 possibilities of termination. Either it will make CO2 or CH3Cl or C2H6, all right? Yes, so with that thing. Yeah, so when I look at this part here with termination, okay, they will occur. Okay, so basically in termination, you guys, it will occur because the 2 radicals will collide together to form an unreactive molecule, right? Like the chlorine dot and chlorine dot, okay? Or chlorine dot and then methyl, the CH3 radical, and then that reacts to make this is CH3Cl, right? That we saw earlier, which is a substituted alkane. And then of course, the last possibility is your chlorine, right? You have two of the CH3s radical. Yeah, that's a little bit messy. I'm sorry, because this is carrying over from this. That CH3Cl plus dot Cl is coming from this one. So pardon me here. This one should be dot CH3 plus dot CH3 makes ethane C2H6, okay, for the termination. All right, I think I nailed that to death. Let's go back a little bit here. Yeah, but anyways, termination stops the reaction. Okay, so with all that, with regards to substitution, okay, it's really hard to control just a single substitution, okay? Because substitutions don't just stop when just one hydrogen, okay, has been replaced. Okay, so they continue until all the hydrogens have been replaced. Okay, so after some time, okay, the CH3Cl molecules will be present, okay, in significant amounts, but they will keep reacting, okay, to form like di and tri and tetra substituted alkane molecules. Now, if you have no idea what that means, these are your, this is your, increase in your prefixes. So I'll show you this. Sorry. You saw that earlier. Let me go to past. Just a second. You know this already, kind of. We did that in the homework sheet last week. Okay, here we go. So what I'm talking about here, okay? This is what I'm talking about here. You see? So they will keep reacting to form, besides just the single carbon one, okay? They will keep reacting to form the di and tri and tetra substituted alkane molecules, right? As you see what happens here. Sometimes they use these names too, just so you know, okay? So in case you're not familiar, you might see alternative names to these. This one, some of these you should know how to name, like carbon tetrachloride. It's just a normal covalent compound naming system. This is methyl chloride. You know how to do that anyways, because that's how we name, your kind of your alkanes, substituted alkanes. These two, I don't think you'll be familiar with it, okay? These are just other names that you don't know. Chloroform is very important. When people kidnap somebody, they use this chemical and then they put it on a little cloth and then you wrap it around someone's nose and they pass out, okay? Let's just say I have some experience with this one. Okay, now, all liquids at room temperature, okay, for these, yeah. And then the heavy chlorine atoms will increase the London dispersion forces. Okay, and then the polar carbon chlorine single bonds, they can have polar molecules. Right. Okay, so let's see. Now, how do we get, okay, out or separate out the one that we want? Well, we'd have to separate them with the process of fractional distillation. Okay, you guys should already know what distillation is, right? Normal distillation is like when you have salty water, seawater, and you want to separate the salt from the water where you boiled it, right? And then the salt becomes stuck in the flask, hopefully, after you heat up the water and evaporates the gas, steam. Then it gets condensed by another chamber in your distillation equipment, right? To cool down that gaseous water to liquid water, again, that's hopefully pure and separate from the salt. That's normal distillation. Now we will look at fractional distillation, which you should have seen these before when you did middle school in MYP. So I'm going to show you now the animation to review what the fractional distillation is, okay? Okay, let me see. Let's go to your board. Just a second, I gotta stop sharing this because I can't even get to the other screen. Always a pain. Why is it not coming out? Uh-oh, I think I might have just left the alkanes, where are you? All right, now back to the animation. Okay, you guys see that, I hope? Sort of. Okay, here we go. Here's fractional distillation, okay? Now, if you learned this in MIP, you should remember that this was something that they introduced you to you briefly, just about how you use it to separate the crude oil that you dig up from underground, to separate them into a lot more useful products, such as gasoline for your cars and stuff, okay? So here's a review of your fractional distillation. So the fractional distillation column has a temperature gradient, okay? It's hotter at the bottom and cooler at the top, okay? Yes, and then throughout the columns are several trays. So crude oil is heated to about 350 degrees Celsius, okay, and pumped into the column near the bottom, okay? And then at this temperature, okay, most of the fractions are gases, and any liquid falls to the bottom of the column, okay? Because, heavier stuff goes down, lighter things go to the top and rise. Okay, so the trays at each level are fitted with a number of bubble caps. You don't really need to know that one, okay? But anyways, they force the hot vapors rising through the column to mix with the liquid that has condensed. And alkanes with a high enough boiling point, okay, condense at that level. Okay, so alkanes with lower boiling points remain as gases and pass up the column to the next tray. And condensed fractions are either piped off or routed back down to a lower level, okay, where they re-vaporize and go through the cycle again. Right? It's been shipped off and sold to whatever application. So alkanes with low boiling points do not condense but pass through all the trays to the top of the column where they are collected as a gas. Okay? All right. So that is your review of fractional distillation. Okay, so now with regard to your substituted ones, let's look at the screen here. Here, okay, with your halogenalkane, here you go. If that makes sense, that's how they would be separated because they have boiling point differences, okay? So when they put into a fractional distillation, they're separated by their boiling point differences, as we just explained for the crude oil example. But yeah, of course, the higher it gets, then the higher the boiling point here. So that's pretty straightforward for you all. Okay. So now to end this, with the other type of reaction that alkanes undergo is combustion reactions. Okay. So you guys already know what combustions are. Okay. So when alkanes, let me just go back to an earlier slide and show you that you can do that example with me. Here we go. Okay, now, so as we know, combustion reactions are one of the 5 types of your chemical reactions, right? We learned them before: single displacement, double displacement, synthesis, right? Decomposition, and then the 5th one is combustion. Right? So here we know that most things are exothermic, and combustion reactions are a very common exothermic reaction. Usually alkanes is your main reactant, right? Such as C4H10 here. And you always react with oxygen, and your main products in a normal combustion are carbon dioxide and water. Okay? Right now, if you have incomplete combustion, right, insufficient amount of oxygen, right, bad ventilation or whatever, then you end up making carbon monoxide, CO, instead of carbon dioxide, CO2. Okay? So, and we know CO is bad because it's poisonous, and you can kill yourself with that if you in a room, with just CO. Okay, it binds to the hemoglobin in your blood and prevents the absorption of oxygen. Okay, so that's just to end this alkane lesson. We will go back to just to make sure you remember how to balance your alkane. Your combustion of alkanes. Okay, now please always follow this rule. You see over here, you always follow the acronym CHO, like a Korean person's last name, carbon, then hydrogen, then oxygen. If you do it in that sequence, you will never get it wrong. Now, I want to just review with you here, and then we'll end this lesson on alkanes. You need to understand, of course, how you balance these. They're not always straightforward because sometimes you have a decimal or a fraction. Okay, so if you're doing a balanced chemical equation for the complete combustion of pentane, okay, let's just go to the whiteboard here. Okay, so let's review how to do this. How did I miss this out? I'm supposed to be going to the whiteboard. Ah, do you see that? I'm not even joking. Let me go again. Okay, here we go. Sorry about that. So the complete combustion of pentane. You should know this general formula by now, what it is, right? Try to get used to using your states of matter, okay? They'll ask you that on some of the questions on your IB test, which some of you are not even good at yet. And you should definitely know oxygen is gas. Oh, sorry, I didn't balance that for you. Okay, can you read that now? Let's do that again. Draw. Let's go to 5, CO2. This is the worst whiteboard ever. It's much easier just do it on by hand and then scan it in. Why am I doing that? I just gave you all the answers. Okay, that's okay. We won't do it next time. H2O. Yes, so okay. Carbon is done first. That's these here. So this is 5, this is only 1, make a 5 over here. Okay. Then we do the H, that's 12 here, and then there's only 2 here. So put a 6 here. Right? And then the oxygen, okay, is what's going on here. Let me see. So this one has 2, and then this one has then 10 plus 6 is 16. Okay, so we need to have 8 here. All right, now that's all done. Good for us. But then now we need to do for butane. Okay, so the next part is asking you, okay, from the PowerPoint to write the balanced chemical equation for incomplete combustion of butane, right? So that's what we're going to do next. Incomplete combustion of butane. God, okay. That's just lovely when I can again. Okay. So C4H10 gas plus O2 gas. Okay. Remember, when they ask you these questions, they don't give you anything. You got to write your equation from scratch, like we're doing here. Okay. So if they say incomplete combustion, you should already know that one of the products is going to be CO. Okay. Carbon monoxide gas, and the other one is still going to be water. Make sense? Now, this water, though, with the incomplete combustion you have, is usually going to be a gas state. That's the tricky part. Okay. All right, now we're going to balance the carbon first, right? So there's 4 carbons here, so I need a 4 over here. And then the hydrogen, there's 10 here, and there's 2 there. So I need to have 5 here to make that 10 hydrogen on both sides. Okay, now we have oxygen. 2 oxygens here, and then you have 4 COs plus 5. That's 9 oxygens on the right side and only 2 here. So the first thing I could do, if I want that to be 9, I would take 9 half times 2. Make sense? which is the same thing as 4.5. But what I don't want is, they don't want you to leave it like this, okay? On your IB test, please don't leave it in fractions. Please do always get whole numbers. So you want to make sure that's not a decimal or a fraction. So all you simply do is you get rid of that part and multiply everyone by 2. This will become then 8. This one will become then 10. Okay? And that is your balance equation for the incomplete combustion of butane. Make sense? All right, so that is the lesson for alkanes, and I will move on to then reactions of alkenes and then alcohols in different videos.